Have you ever, found yourself holding a thick stack of medical reports, maybe like multiple blood panels stretching back years, and you just feel that immediate cognitive overload?
Oh, absolutely. It happens all the time.
It's not just one number you're looking at, right?
Yeah.
You have to find your hemoglobin, maybe your various platelet or cell counts, and then you have to painstakingly cross-reference every single one against a specific reference range.
And those ranges can vary depending on the test, the lab.
Exactly. And then the real work starts, trying to track how those numbers have, shifted or trended over time. It's just so dense and complex.
It really is. And that density, that complexity, makes potentially life-saving information feel almost completely inaccessible, even for trained professionals who are just pressed for time.
Right.
And that's really the core challenge in modern healthcare, isn't it? This problem of, underutilized data. These reports, they're foundational documents. They've got valuable insights into a patient's history, their physiology. But actually interpreting them demands this huge amount of focused, specialized human effort. You're constantly cross-referencing, analyzing relationships between different parameters, spotting trends over time.
It's a lot.
It is. So today, we're embarking on a deep dive into a conceptual solution for this exact problem: a medical reports analysis dashboard. Our mission here is to really unpack the architecture of this thing.
Okay.
We want to show how these cutting-edge generative AI and cloud technologies are being used to turn that static, complex data into something dynamic, something actionable, insights that could dramatically speed up clinical review.
And it sounds like we're dealing with a really powerful, a three-way convergent solution here. It's like a specialized stack built just for this task.
That's a good way to put it.
We've got Amazon Bedrock, which provides the large language model intelligence that's kind of a brain, right?
Right, the core intelligence.
Then there's Langchain, handling all the complex orchestration, the document processing, managing context, like the nervous system connecting everything.
Precisely. It's the coordinator.
And finally, Streamlit, delivering that clean, intuitive, real-time user interface, the face the user actually interacts with.
Exactly.
So for you, our listener, whether you're, say, prepping for a technical meeting on AWS architecture, or maybe you're just curious about how AI is starting to revolutionize healthcare workflows, our goal is to explain not just that this collaboration works, but how this powerful convergence is actually engineered, how it handles sensitive medical data securely and intelligently.
Okay, let's start by drilling down into the problem itself. Our sources are really clear that medical data is often underutilized. Why is that? If the reports are right there in the patient's file, why does the complexity create such a massive bottleneck? Well, it really comes down to two things: cognitive load and time. When a clinician, reviews a report, they aren't just looking at isolated data points. They're performing relational analysis, often under a serious time crunch.
Right.
Take a simple example. Let's say a report shows a patient's hemoglobin is 13.8 grams per deciliter, or GDL. Now that number, 13.8, it's pretty much meaningless without context.
Okay.
The clinician has to instantly recall, or maybe look up, that the normal reference range is, let's say, 13.5 to 17.5 GDL for this specific test.
So 13.8 is technically normal, but it's right there at the low end.
Exactly. It's normal, but borderline low. And that's just one single parameter, one piece of context.
Just one piece of the puzzle.
Right. Then the human mind has to take that 13.8 GDL and interpret it in the context of, say, the red blood cell count, the MCV, that's mean corpuscular volume, maybe the patient's iron levels.
Ah, okay.
Because if the RBC count is high but the MCV is low, that tells a very different story than if both are sort of smack in the middle of the normal range.
Right, different clinical implications.
Absolutely. So analyzing those internal relationships, comparing them against established medical knowledge, and then tracking them across reports from maybe January, then July, then the current month, that's where the human effort just skyrockets.
I can see that.
This kind of specialized interpretation, it's just very time-intensive. It demands constant focus. And, well, let's be honest, it's prone to human error when clinicians are overworked and juggling multiple patients.
So the core ambition of this dashboard, the solution we're talking about, isn't just to pull up a number. It's meant to act more like an expert assistant.
That's the idea.
Moving beyond just static reports to offer dynamic analysis through, natural language and visuals.
Precisely. The goal is really to enhance how the healthcare provider interacts with the data. And this is accomplished by leveraging those three key technologies we mentioned earlier.
Okay, let's recap those. Amazon Bedrock.
Bedrock provides the large language models, the LLMs. That's the engine that understands, interprets, and synthesizes the data using medical terminology. It kind of gets that high neutrophil count and potential bacterial infection are related concepts, even if they aren't right next to each other in the text.
That makes sense. And Langchain, that's the orchestration layer. It ensures that this advanced understanding gets applied accurately to the specific patient's files.
Langchain is absolutely the glue here. It's the critical piece that manages the document processing, coordinates retrieving specific data points, and, crucially, ensures the AI maintains conversation context.
Ah, the context. That seems vital in a medical setting.
Oh, it's invaluable. Langchain's ability to manage that context, making sure the AI remembers the patient, remembers the specific report you were just talking about 5 minutes ago, that eliminates so much repetitive data entry and really streamlines the whole dialogue.
And Streamlit then is the user-facing application. It makes all this complex back-end stuff feel, well, conversational and intuitive.
Exactly. It's the window into the system. But what's truly fascinating about this architecture, I think, is the intentional flexibility built into that AML layer, specifically around model selection.
Meaning it's not locked into just one AI model.
Correct. And that's paramount in a field like generative AI that's evolving so incredibly fast, you don't want to be locked in.
That model choice does seem strategic. You're saying you can choose from like a whole menu of different high-performance LLMs available through Amazon Bedrock.
That's right.
Our sources specifically mention choices like the Anthropic Claude series, maybe the big one, Opus 4.1 or the faster 3.7 Sonnet, or even the Amazon Nova Foundation models like Nova Pro or Nova Lite. For a clinician or maybe a hospital administrator, why should they care about having a choice of AI engine under the hood?
Because this model flexibility allows organizations to tailor their resources very specifically to the clinical need. It lets them balance those crucial factors: accuracy, speed, and of course, cost.
Okay, can you give an example?
Sure. Imagine a scenario involving a really complex, maybe a rare disease case. Maximum accuracy and nuanced interpretation are absolutely essential. Perhaps it's a specialized oncology report.
Right, high stakes.
Very high stakes. In that instance, the organization might choose to use a top-tier high-end model like Claude Opus or maybe Nova Pro. It might be a bit slower, maybe more expensive per query.
But the reliability justifies it.
Exactly. The increased reliability in that specific critical context justifies the cost and potentially the slightly longer wait time.
And then conversely, what about for like high-volume routine screenings or wellness checks?
Yeah, for those routine reports where the main goal is maybe fast, high-volume anomaly detection or just standard data retrieval, you really need speed and cost-effectiveness.
Makes sense.
So here, a lighter, faster model, like maybe a Claude Sonnet or one of the Nova Lite models, would probably be preferred. The architecture is designed to support this kind of strategic optimization.
So it's not just functional, but also financially viable and optimized for the specific clinical task at hand.
That's the key.
Yeah.
It's a massive step up from a sort of one-size-fits-all AI solution, which often doesn't fit anything perfectly.
Okay, let's unpack this architecture a bit more. Let's move from the clinical benefit to the technical mechanics. For our listeners who love to see how things actually work under the hood, our sources detail a pretty clean 4-layer structure. Understanding this, I think, helps us grasp how all these moving pieces really cooperate.
Absolutely. Think of it like we're dissecting a sophisticated machine. We start right at the foundation, which is the storage layer.
Okay.
This is where the raw patient data has to be stored, obviously with maximum security. So medical reports are securely housed in Amazon S3.
S3, right. Standard cloud storage.
Standard, but highly secure and durable. The sources mention them being stored as CSV files, like the basic.csv used in the demonstration, containing all those crucial parameters. S3 provides the durability and security you absolutely need for immutable medical records.
And importantly, this storage layer isn't just holding the raw patient data itself, is it? It also holds the systems like short-term memory.
Correct. That's a critical point. This layer also securely includes the conversation buffer memory.
Ah, okay.
This is basically where the transcript of the current chat session resides. It's what ensures the AI remembers the question the user just asked 5 seconds ago or 5 minutes ago.
Got it.
It's really the foundational component for the system's context awareness, making the whole conversation flow naturally instead of starting fresh with every query.
Okay, so moving up from storage, we get to the heart of the system, the intelligence layer.
That's the AML layer. Now, this features Amazon Bedrock, which provides the literal LLM intelligence we talked about. But To translate that raw text data into knowledge the AI can actually search and understand quickly, two other elements are really key here.
Which are?
Amazon Bedrock embeddings and the in-memory vector store. This is where we make the shift from just searching text to actually searching concepts.
Okay, let's pause there for a second because terms like embeddings and vector store, they're crucial, but they can be a bit abstract. How do we explain what an embedding is to someone who might not be an AI specialist?
Yeah, good question. Think of an embedding as translating a word or maybe a complex medical concept like, say, hemoglobin, into a highly specific set of coordinates, a numerical vector, basically in a multidimensional space.
Okay, coordinates.
And this translation process is very sensitive to meaning. So if we generate an embedding for the word anemia and another embedding for the phrase low red blood cell count, those two numerical vectors, those coordinates, will end up being positioned very close to each other in this abstract mathematical space.
Because they're related concepts?
Because there are semantically related concepts. In contrast, the embedding for, I don't know, tree would be numerically very, very far away.
Okay, so an embedding turns medical jargon, synonyms, related ideas into essentially numerical proximity. And the vector store is just where all these coordinates are kept.
Exactly. The in-memory vector store is a specialized kind of database. It's organized specifically to hold these vector coordinates efficiently. And this is way more powerful than a simple keyword database.
Oh, so?
Because when a user asks a question, the question itself is also converted into an embedding, into coordinates, and the system then searches for nearby, conceptually relevant vectors in the store.
I see.
This allows the AI to find the answer, even if the patient's report uses slightly different terminology than the clinician's actual query. It gets the meaning, not just the keywords.
That makes sense. And that leads us directly to the next layer up, the processing layer. This is essentially the orchestration and retrieval brain, and it's powered primarily by Langchain, right?
The processing layer manages this complex dance between the storage layer and the intelligence layer. It handles Langchain document processing, which means taking that raw CSV report, slicing it up into manageable chunks, and then sending those chunks to Bedrock to create the embeddings we just talked about, which then gets stored in the vector store.
Right.
And crucially, it manages the conversation retrieval chain. Now, this chain is responsible for fetching the most relevant data snippets, those chunks, from the vector store based on the user's actual question.
Okay.
And then it provides only those specific verified facts to the LLM for the final response generation.
Right.
It doesn't just let the LLM access everything at once. It also handles things like data parsing to structure the output cleanly for the user.
Okay, hold on. If we're relying on an LLM for some pretty complex relational analysis, how do we absolutely guarantee it doesn't, invent a relationship or hallucinate a data point, especially when we're talking about medical data where a diagnosis could potentially be on the line?
That is probably the most critical question, especially in a medical context.
Yeah.
And the answer lies in the retrieval augmented generation, or RA, framework that this processing layer enforces.
Okay.
That retrieval chain we just mentioned, it's designed precisely to mitigate hallucination. The LLM, the generative model, it never operates in a vacuum, just relying on its general vast training data.
Right.
Instead, the retrieval chain ensures that when a query comes in, the system first finds verifiable patient-specific facts, those relevant vector chunks from the report, and it augments the LLM's prompt with only that verified source material.
So it gives the LLM only the relevant facts from the actual report to work with.
Precisely. The LLM's job then shifts. It's not about generating knowledge from scratch. It's about synthesizing and interpreting the provided factual data snippets from the patient's own record. This grounding in the patient's index reports is what builds trust and ensures accuracy.
That clarity is absolutely vital. Okay, so the facts are anchored securely in S3, they're indexed conceptually in the vector store, and then they're carefully retrieved by Langchain before the LLM even sees the question.
That's the flow.
And finally, that brings us to the top layer, the user interface layer.
Yes, this is the user's window into all that complex processing happening underneath. It's the Streamlit web app. It provides the interactive chat interface we've talked about, and very importantly, the dynamic Plotly data visualizations.
Got it.
It basically translates all those numerical coordinates and the synthesized text coming from the processing layer back into something readable, understandable, and actionable for the clinician.
Okay, let's try and trace the journey of a single data point, or maybe a query. Say I want a new report, and then I ask a question about a trend in that patient's data. What happens step by step?
Okay, so first, that new report gets securely stored in Amazon S3. Then, Langchain's document handler immediately gets to work. It chunks the text, sends those chunks to Bedrock to create the embeddings,
Hmm.
which are then stored in the in-memory vector store, indexed for meaning. Now, when you, the user, enter your query through the Streamlit interface, let's say it's, show me the trend of this patient's platelet count over the last year.
Okay.
The Streamlit front end sends that query down to the processing layer. Langchain first checks the conversation buffer memory for any relevant context from earlier in the chat. Then it converts your query, platelet count trend, into an embedding.
Right, the coordinates.
It searches the vector store using those coordinates to find all related platelet data points across all the available reports for that patient within the specified time frame, say the last year.
Got it. Finds all the relevant pieces.
Yes. Langchain then bundles those relevant numerical values and maybe some contextual snippets, and it passes just that bundle to the Amazon Bedrock LLM.
Along with the original question.
Exactly. The LLM then interprets the trend based only on that provided data, understands the context, maybe notes if it's increasing or decreasing, and the final response, which might include a Plotly trendline visualization showing the platelet count over time, is rendered back to you via the Streamlit interface.
Wow. That holistic view of the data flow really emphasizes the complexity being managed here. Now, just quickly on the technical setup, the sources really stress the prerequisites, including the mandatory use of a Python virtual environment, venv. Why is isolating the dependencies so critical for a system like this, one handling medical data?
Yeah, for any technical listeners out there, using a VIN is absolutely non-negotiable. It's a fundamental best practice for ensuring stability and reliability in any serious application, but especially here.
Why especially here?
Because when you deploy a production-grade system, particularly one handling sensitive patient reports, you simply cannot afford package conflicts or unexpected versioning errors popping up.
Right, that could break things badly.
Terribly. A virtual environment ensures that the specific versions of all the required Python packages, like Bodo 3 for talking to AWS, Pandas for crunching the data, Langchain Oz for the orchestration, Streamlit itself, are completely isolated from the rest of the system's libraries on the server.
So it keeps everything clean and separate.
Exactly. It guarantees a clean, consistent, and stable environment, which is paramount for deployment and absolutely essential for maintaining the integrity and reliability of the application when you're handling compliance-heavy workloads like healthcare data. It just minimizes those nasty, unforeseen deployment errors down the line.
Okay, so we've established this robust, secure architecture. Let's shift focus now entirely back to the clinical frontline. How does this system actually translate all that underlying intelligence into an immediate, tangible benefit for the doctor or the clinician using it? It seems like it's all realized through that context-aware chat interface.
Yeah, that interface really changes the nature of the dialogue a clinician can have with patient data. Because Langchain is managing that conversation buffer memory we talked about, the system effectively maintains a conversation history within a session.
Right. It remembers what you just asked.
It remembers. And that means the user can seamlessly transition from asking for basic data retrieval, like what's the potassium level, to asking for really complex relational analysis without ever having to constantly restate the patient context or point back to the specific report they're looking at.
So it moves beyond just looking up static numbers in a report.
Absolutely. It moves from that static report review process to something much more like a genuine interactive consultation with the data itself.
Our sources give a really brilliant illustration of this sophistication, using a kind of three-step query sequence. Let's maybe dissect the clinical implication of each of those steps. The first query is the simplest. What is the hemoglobin level in the report?
Right. That's the straightforward starting point. It's pure data retrieval. The system confirms a specific value. Let's stick with our 13.8 GDL example. And importantly, thanks to that RAG mechanism we discussed.
Retrieval augmented generation.
Yes. The system can usually cite exactly where in the source report it found that fact, building trust. But the real sophistication starts to emerge in the second query.
Okay, and that second query is, how does this compare to other parameters in the report? Are there any that stand out? Now, this requires relational memory, doesn't it?
Exactly. The system instantly knows that this refers back to the 13.8 GDL hemoglobin level you just asked about.
Yeah.
It doesn't need you to repeat hemoglobin. It then analyzes that specific number in relation to the entire report context, looking at the red blood cells again, the iron levels, comparing against all the reference ranges, and it flags any parameters that are maybe outside the normal boundary or perhaps approaching a concerning limit.
So it might find connections the user hadn't explicitly asked about?
Precisely. For example, it might respond by saying something like, okay, the hemoglobin is within the normal range, but note that the mean corpuscular volume, MCV, is slightly depressed, which could potentially indicate a microcytic pattern developing.
Ah, okay.
This kind of comparison and intelligent flagging is traditionally a manual, time-consuming cognitive step for the clinician. Here, the AI performs it almost instantly.
And then there's the third question, the really complex analysis request. This one truly showcases the LLM synthesis capability. Can you analyze the distribution patterns of percentage-based measurements versus absolute values in this report, and identify any notable patterns in their reference ranges? I mean, that sounds like something a medical statistician might spend a good hour generating.
It is definitely a high-level, quite nuanced request. But in a clinical setting, especially when looking at something like a complete blood count, CBC, with differential, this kind of analysis is essential.
Why is that distinction between percentage and absolute values so important?
Well, in a CBC differential, you get absolute counts, like the total number of white blood cells, WBCs. But you also get percentage counts, like the percentage of those WBCs that are neutrophils or lymphocytes and so on.
Okay.
Now, percentage measurement can sometimes be skewed if the absolute total number is very low or very high. So the clinician really needs to know if the relationship between those two types of measurements, the absolute count and the percentage breakdown, is clinically consistent and makes sense.
Can you give an example?
Sure. Is the percentage of lymphocytes high just because the overall white blood cell count is abnormally low? Or is the absolute number of lymphocytes actually elevated, maybe suggesting a significant immune response like fighting a viral infection? They tell different stories.
I see. So asking the LLM to analyze the distribution patterns and the reference ranges for both types of measurements together provides a kind of holistic check.
Exactly. It's a check on the quality and consistency of the data, helping ensure the clinician isn't potentially misinterpreting a relative anomaly as if it were an absolute one or vice versa. That's a really deep clinical insight, and here it's delivered almost instantly.
And critically, this sophisticated synthesis isn't just delivered as, like, a big wall of text output, right?
Right.
Which would still take time to parse.
No, and that's key to the efficiency gain. The Streamlit interface leverages dynamic visualizations built using Plotly, and these dramatically accelerate comprehension.
Yeah, when you're dealing with potentially life and death data, speed and clear comprehension are just everything. Why are visuals so indispensable here? What do they add beyond the text?
They transform the data from just abstract numbers on a page into immediate, intuitive visual patterns. Instead of reading 13.8 falls between 13.5 and 17.5, you literally see the results placement relative to the normal range instantly. Our sources highlight 3 specific types of visualizations that are really instrumental in achieving this speed and clarity.
Okay, what's the first one?
The first is the range comparison chart. This is pretty much mandatory for any good medical dashboard, I'd say.
How does it work?
It visually plots the patient's actual measured value right alongside the defined normal reference range for that specific test. So if the patient's value sits clearly outside that healthy band, the anomaly is immediately obvious, maybe even color-coded.
So you get instant visual confirmation that something needs attention.
Exactly. Without the clinician having to read a single number or text box carefully, just a glance tells them if it's in or out of range.
Okay, that makes sense. Next up is the standard bar chart.
Yep, good old bar charts. They're excellent for doing side-by-side comparisons of multiple different numerical parameters within a single report panel.
How would that be used here?
It allows the clinician to quickly assess the relative magnitudes of different lab values across the entire panel, which is crucial for that internal relational analysis we talked about seeing just visually if the red blood cell count looks disproportionately low compared to, say, the platelet count on the same report.
Got it. Comparing relative levels quickly. And finally, maybe the cornerstone of longitudinal patient care, trend lines.
Trend lines are arguably the most impactful visualization feature for ongoing patient management, especially over multiple visits or reports.
Why is that?
Well, if a patient's condition is stable regarding a certain parameter, the trend line will be flat or maybe fluctuate normally. But if, say, a patient's creatinine level is slowly, almost imperceptibly increasing over 3 or 4 quarterly visits, a subtle pattern that might be easily missed when flipping through static PDF reports one by one.
Right, you might not connect the dots easily.
Exactly. But a trendline visualization will clearly highlight that upward trajectory. It makes the pattern jump out at you. This is powerful because it's predictive. It enables proactive clinical decision-making.
Allowing interventions before a critical threshold is crossed.
Precisely. This combination, The context-aware chat plus these dynamic targeted visualizations is what elevates the system far beyond just being a simple database query tool. It becomes an analytical partner.
Okay, anytime we talk about putting generative AI anywhere near sensitive medical data, the conversation has to immediately pivot to security, compliance, regulatory adherence. I mean, the stakes are just incredibly high.
Absolutely. Non-negotiable.
So, since this system is designed to handle actual medical reports, what are the absolutely crucial guardrails that must be configured within that Amazon Bedrock framework?
Security is paramount, as you said.
Hmm.
It's really the foundation of trust for any AI in healthcare. The Amazon Bedrock Guardrails feature is an essential safety layer. It gets configured before the model even begins processing any queries.
Okay. And what's its primary function?
The absolute non-negotiable limitation that has to be enforced by these guardrails is that the model must be strictly restricted from providing medical advice, offering diagnoses, or prescribing treatments.
That seems critical.
It is. The system is designed purely as an analysis and interpretation engine. Its job is to interpret the data that's provided, spot patterns, answer questions based on the facts in the report. It cannot and must not replace the clinical judgment of a qualified human provider.
So how exactly do those guardrails function? Is it just like a setting you tick, or is it more active?
It's more active. Think of it as a two-stage filter. First, the guardrails scan the user's input query itself. They check for any phrasing that looks like it's asking for advice or a diagnosis, something like, tell me what disease this report indicates.
Okay.
If phrasing like that is detected, the query can be blocked right there before it even goes to the LLM. Second, and this is crucial, the guardrails also scan the AI's generated response before it's delivered back to the user interface.
Ah, so it checks the output, too.
Yes. It checks for any forbidden content, like phrases such as, you should probably take X medication, or this pattern confirms diagnosis Y. If the AI, for whatever reason, attempts to generate that kind of restricted content, the guardrail intercepts it.
And what happens then?
It replaces the AI's potentially harmful response with a pre-approved safe refusal statement. Something like, I can analyze the data in the report, but I cannot provide medical advice or diagnoses. This maintains those strict functional boundaries.
Interpreter, not diagnostician. That distinction is vital. Now, if this dashboard moves from the demo stage, using dummy data, into a real-world production environment in a hospital or clinic, it absolutely has to be high PR compliant.
100%.
What are the stringent security measures required for that kind of real-world deployment beyond just the AI guardrails?
Okay, yeah. Real-world security is multi-layered and must adhere strictly to HIPAA's requirements for protecting electronic protected health information, or EPHI. This mandates not only those stringent access controls, usually via IAM rules.
IAM being Identity and Access Management from AWS.
Correct. But it also demands comprehensive audit trails and robust encryption policies, both for data at rest and data in transit.
Let's break that down. Data at rest.
For data protection at rest, we absolutely require Amazon S3 server-side encryption. Specifically, SEC S3 is often used. This means the data, the actual medical reports, are encrypted automatically as soon as they hit the S3 storage layer. The encryption keys are managed securely by AWS, providing strong protection against, say, unauthorized physical access to the underlying storage infrastructure.
Okay, so the files themselves are encrypted on the disk. What about securing data while it's moving around in transit?
Equally important, any data moving between the different components between the user's browser and the Streamlit application, between Streamlit and Langchain, between Langchain and Bedrock, all of that must be protected using Transport Layer Security, or TLS, basically HTTPS.
Standard web encryption.
Standard, but essential. If the data is moving over any network, internal or external, it must be encrypted to prevent eavesdropping or interception. Patient reports have to be protected at all stages of the workflow.
And we also have to talk about PII, personally identifiable information that might be within the reports themselves. Names, dates, medical record numbers.
Yes, PII protection is absolutely paramount under IPAY. This often involves applying techniques like data masking or even de-identification to specific PII fields like patient names, addresses, maybe specific dates of birth, especially when the data is being processed by the LLM, just to minimize exposure.
Okay.
And furthermore, underpinning all access, we must enforce the principle of least privilege using those AWS IAM roles.
Explain that principle quickly.
It's the foundation of secure access control. It means a specific healthcare provider or maybe an analyst using the system only receives the absolute minimum level of access permissions to access only the specific S3 bucket needed and only the specific API calls required to perform their legitimate function. No overly broad or blanket access is ever permitted.
Got it. Granular control. Now, the source has also outlined a pretty detailed security checklist specifically for the S3 configuration itself, underscoring that the container holding the data must be rigorously hardened.
Hmm.
What specific S3 configurations absolutely must be locked down?
Yeah, there are several critical S3 security actions mentioned. First, you absolutely must enable versioning on the S3 buckets storing the reports.
Why versioning?
It's essential for audit trails, but also for recovery. It protects against accidental deletions or even malicious modifications by maintaining a complete history, a record of every iteration of every report file.
Okay. Crucial for data integrity. What else?
Second, and this is fundamental, block public access must be enabled, period, both at the individual bucket level and ideally at the entire AWS account level. There can be absolutely zero chance of public exposure for sensitive health data stored in S3.
Makes sense. And third?
Third, you need to implement strict S3 bucket policies. These are rules applied directly to the bucket that enforce specific conditions. For example, a policy should mandate that encryption, like SSE S3, is required for all objects uploaded, and it should explicitly limit access exclusively to specific, pre-approved IAM roles or users. No one else gets in.
So these layered technical measures, they work together to ensure the medical reports are protected from the moment they're uploaded.
That's the goal, defense in depth.
Now, beyond just immediate data protection, meeting compliance standards like IPA requires comprehensive monitoring and accountability. That means rigorous audit logging, right?
Precisely. Accountability relies entirely on having a perfect, immutable record of activity. Activating AWS CloudTrail is absolutely essential for this. CloudTrail logs basically all API calls made across your AWS environment.
What specifically needs to be logged for this application?
The CloudTrail logs must capture all S3 data access events. That means tracking exactly who accessed which report object and precisely when. It also needs to log every single Amazon Bedrock API call made by the application and capture all IAM user and role activity related to accessing these resources.
So you have a complete trail.
You have a complete verifiable history. These CloudTrail logs provide the immutable record needed to meet regulatory audit requirements, and they're also crucial for security monitoring, helping you quickly identify any anomalous or potentially suspicious activity. This ongoing monitoring capability is absolutely central to maintaining IPI compliance over the long term.
Okay, so assuming an organization successfully implements this secure, compliant foundation, how can they then take it further? How can they enhance the intelligence of the system for maybe more specialized clinical use cases?
Right, once that security bedrock is solidly in place, organizations can definitely pursue specialization, and that's where the value of the AI can increase dramatically. The primary path here is usually fine-tuning the foundational model.
Fine-tuning, what does that involve?
It involves taking one of those base LLMs available through Bedrock and training it further, specifically on the organization's own data. This could be proprietary medical data sets, internal clinical protocols, nuanced terminology used only in that hospital system, or specific regional domain expertise.
So you're teaching the general AI about your specific context.
Exactly. This process elevates the LLM's understanding from general medicine to specific institutional knowledge, and that allows it to provide much more contextually relevant, accurate, and useful analysis for that organization's specific needs.
That sounds powerful, but also like potentially a massive undertaking, training an LM internally, even with fine-tuning. Is there maybe a way for specialized organizations to get a head start on that?
Yes, there often is. Organizations can frequently leverage pre-trained medical LLMs that are already available through the AWS Marketplace.
Ah, okay.
These are models that have already been optimized by third parties for various specific healthcare use cases, maybe things like radiology report interpretation or analyzing pathology notes, and they often come with pre-vetted compliance considerations built in.
So you could potentially bypass some of the initial training effort.
Right. Choosing a suitable marketplace model allows an organization to jump straight to highly specialized functionality, bypassing much of that initial foundational fine-tuning effort, while still needing to ensure it adheres to their own strict data governance and security requirements, of course.
Wow, this has been a truly comprehensive breakdown of the technology and the implications. If we look back at our deep dive today, this medical reports analysis dashboard concept, it really does seem to successfully transform what used to be an incredibly complex, highly time-intensive process.
That manual interpretation.
Yeah, interpreting countless numerical parameters,
Hmm.
cross-referencing reference ranges, spotting trends, it turns that into a much more streamlined, intuitive, and frankly, highly efficient workflow.
It really aims to.
And this is achieved through that integrated power of the LLMs via Amazon Bedrock, the crucial context management and retrieval sophistication from Langchain's RRED framework, and then the interactive visibility provided by Streamlit and those Plotly visualizations.
And critically, this integration isn't just about making things faster or easier. It's fundamentally about building on a robust, secure foundation first. The architecture, with its strict reliance on IAM for access control, S3 encryption for data protection, CloudTrail for logging, and those mandatory Bedrock guardrails.
Right, the safety nets.
Those provide the essential framework necessary for building compliance-aligned healthcare applications people can actually trust. It fundamentally aims to shift some of the interpretive burden away from the clinician.
Freeing them up.
Exactly. Allowing them to spend less of their precious time just synthesizing raw data points and hopefully more time focusing on proactive patient care, communication, and overall clinical strategy.
We started that last section 4, by talking about that absolute guardrail, the fact that the AI as it stands today cannot and must not provide medical advice or diagnoses.
Right, the hard line.
And that limitation is absolutely essential for safety and trust right now. But thinking ahead, given the advancements we've detailed just in this conversation, the potential for highly specialized fine-tuning, the sophistication of the RAG framework that guarantees factuality based on source documents, and the relentless hardening of security and compliance standards.
The trajectory is clear.
Consider this final thought for you, our listener. What specific, measurable advancements in, say, ethical validation frameworks, in fail-safe safety protocols, and maybe in deep clinical integration and testing would the healthcare industry realistically need to achieve before it could even begin to cautiously consider relaxing those strict limitations? Before AI could potentially move even slightly from being purely a data interpretation tool towards becoming a truly supportive element in diagnostic capabilities. That's the frontier you have now explored with us, and perhaps something worth mulling over.